So, a warm good morning to all the audience of Equinox. It's great to have you back again for our next talk in the series of Developer Weekend. So, today it's a very special talk, and for that we have Mr. Ben Dechrai, technologist, public speaker, community and developer advocate of Auth0, who will be speaking on hacking JSON Web Tokens. He is a technologist with a staunch focus on security and privacy. He takes deep technical he takes deeply technical topics and engagingly slices them into digestible portions. He helps audiences understand the topic, the motivation for the approach to the topic, and this is the hard part, how to do something quite technical to a professional standard and really understand why it works the way it does. It's always a pleasure to host Ben at Equinox. So Ben, thank you again for coming and over to you.
Thanks for having me. It's great to be here. I have to say, it's not often that a conference or a hackathon will write their own intro for a speaker, and what you wrote about me is really nice to hear. I love to help communities in that way. I have to say that today is probably not going to be so much about breaking something down to understand how it works. We're going to be working out how to break things, which is potentially a bit more fun, different kind of learning, but we're going to have fun anyway. So before we get started, some of you, probably most of you, have probably never met me before. So I just want to have a quick chat about why I'm here talking to you about this today and not somebody else. So my background, I've been a software developer now for over 21 years. I think actually it's almost 22 years. And in all that time, I've been really passionate about security and privacy and advocacy, civil liberties, all of these kind of things. So I've been a staunch supporter of making sure that the end user is always looked after. As well as that, I've been really involved in the developer and open source communities. I've run conferences in Australia and I've spoken at places around the world. I love to connect with communities and developers and learn what challenges they're facing and see if there's any way that I can learn from them or maybe I can help them. And the culmination of these two, the passion around security and privacy and loving connecting with communities, meant that this guy once that I met who worked for Auth0, and he was a developer advocate, and he persuaded me to interview and take a job. So I went through the interview process and was offered a job, and now I'm a developer advocate for Auth0, which means I'm able to take my passions and actually bring them into my day-to-day life. So I'm really happy to be here to connect with you all and to share with you a story today about how you can hack JSON Web Tokens and when they can go wrong. At any point, you're welcome to reach out to me. My DMs on Twitter are open. I'm also on LinkedIn. I'm probably the only Ben Dechrai in the world, so I shouldn't be too hard to find, which is possibly a little ironic for somebody who's into privacy. But it shouldn't be too hard to find me. We'll also be having an AMA after this over in Discord, so I'd love for you to jump over to there, and we can have a chat and go through any Q&As that you might have. So before we look at how to hack JSON Web Tokens, let's remind ourselves, or for some of you maybe have a look for the first time, into what a JSON Web Token is and what its purpose is. And predominantly a JSON Web Token, while it can be used for many different things, it was designed in order to support a mechanism for transmitting information around identity and authentication. And it's based on the OAuth 2.0 protocol and the OpenID Connect layer that sits on top of that. So the way this works, really basically, we won't go into the full flows, is you've got a user, you've got the, if I grab my mouse over here, there we go. You've got the user over on the left side here. You've got what we refer to as a relying party. This would be your web application that somebody's trying to log into. And then you've got the identity provider. And the user is able to make a request to the web server for some kind of information. And in this case, it's going to say, look, we don't know who you are yet. So the request that comes in is then turned into a redirect back to the identity server, at which point I, as a user, am then required to log in. The identity server then sends an authorization code, which back as another redirect, which then ends up on this relying party, or the server that has the resource that I'm after. And this relying party can then make a request to the identity server with that authorization. You tell me who you issued that to, so that the credentials, or not the credentials, but the identity tokens never get sent back via the user, because as we might all know, the browser the web browser over here on the left-hand side is an untrusted environment. So what we want to do is allow the web server to make a request directly to the identity server with this authorization code. And in return, the identity server is going to send 2 or 3 tokens. The identity token is a JSON Web Token, and we'll have a look at what a JSON Web Token looks like in a second. And that tells the application that I've just logged into a little bit about me as a person, my identity. The second one is an access token. This allows the web application that I've just logged into to use that token to get information from another system, for example. This is the authorization part. This token allows the web application I've just logged into to do something with another system, excuse me, on my behalf. The access token is frequently a JSON Web Token as well. It can also be an opaque token, which if any of you have done any kind of API communications, you might be familiar with an opaque access token, which is a long cryptographically randomly generated string that has absolutely no meaning. We'll only be looking at JSON Web Tokens today. I won't go too much into what the opaque tokens are. We don't need to know that for today's talk. The third one is a refresh token. So in the instance where you get an access token, the access token will have an expiry, which is a security feature. But if the access token expires, then optionally, depending on some configuration settings, the application will have access to a refresh token, which can only be used with the identity server. So this refresh token here only ever gets sent back to the identity server. And the request for that is, I would like to refresh my access token. Here's a refresh token. Please give me a new access token because the one that I had before has just expired. So those are 3 main tokens. Sometimes that refresh token isn't returned. It depends on a number of factors. But we'll be looking at the ID token and the access token, and specifically the JSON Web Token versions of those. So what is a JSON Web Token? Essentially, it does, well, many things, but 3 of the main things are it's a way of passing around one or more claims or assertions. So a claim or an assertion could be in an identity token, for example, the identity of this person, the name is Ben, or the expiry of this token is tomorrow, or the issuer of this token is auth0. So there are a number of claims that are in JSON that can be read by any system that can decode base64 URL encoded strings, which human brains aren't very good at doing. But the point is they're in plain text, essentially. And that JSON can then be consumed and used by whichever system has received the tokens. The signature component, so there are 3 parts. The signature component means that the recipient of the token can detect if there's been a modification. So obviously, if I've got a claim in there that I'm a member of the admin group, we need to make sure that I haven't added that in at some point, or there hasn't been some kind of modification of the JSON Web Token. Because the JSON Web Token can be verified by the application that's receiving it, we need a signature to verify that nothing's changed since the token was generated. And we'll look at a bit more about how that works. And then, as I've mentioned already, an ID token is ideal for a person's identity. You could think of this as a government-issued ID card or a driver's license or a passport or something like this, where there's information about a person and there's a way of verifying that that hasn't been tampered with. And then you've got an access token, which is more like a permission slip. The application server that I've just logged into has got a permission slip to, for example, talk to a third-party API on Ben's behalf in order to retrieve a contact list. So it can be quite specific in terms of what is allowed to be done with that access token. So let's dive into the inside of an access token. What does it actually look like? Well, we have a header, we've got a payload, and we have a footer. These 3 strings are separated with a full stop for ease of breaking it down again. And they are all base64 URL encoded versions of some kind of content. In the case of a header and a payload, it's base64 URL encoded JSON. So if any of you in the audience are able to do this in your head, you can probably work out what's in the header and the payload right now. We'll show you on the next screen, so you don't actually need to go off and look into this. The signature is then based on the header and the payload, and there are a number of different algorithms that can be used to create a signature. We'll look into that as well. So let's have a look at the header. So if we do base64 URL decode the header that we had on the previous screen, you'll get this JSON out. And basically what it's telling us is that the algorithm used to generate the signature is HS256. The H stands for HMAC, S for SHA, 256. So we've got HS256, HS384, I think, HS512, then there's RS, which is RSA, and we'll look into what some of the differences of these are. But there's a number of different algorithms that can be used, and the header will tell you which algorithm has been used for the signature. And we also have a type. Now, in this case, the type is JWT, which might seem odd because you have to assume it's a JSON Web Token to decode it and then find out that it is a JSON Web Token. But this can then be extended, and I believe there are some plans to do things like JWT plus access tokens. You can actually define more granularly what the type of the particular particular JSON Web Token you're looking at is. But for most intents and purposes, at the moment, we can ignore the type. But it's a common one that's in there that you might see. If we then look at the payload, so this is the string that we had 2 screens ago. If we decode that, then we get a number of claims here. So there's a claim that the subject is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. For those of you who haven't used JSON Web Tokens for any kind of authentication yet, once your user has logged into an identity provider, the application you're writing will receive this JSON Web Token back. Normally, in your application, you would have a table with a username and password in it, a user table with a username and password. In this case, you don't need those credentials in there. That's the whole point of using an identity provider. They will do all of the hard stuff for you. And instead of username and password in your user table, you just store the subject. So every time I log in, or in this case, John Doe logs in future, this same subject will always come back. It also makes a claim that the person who just logged in is called John Doe, and that the token was issued at, IAT, issued at this epoch timestamp. There can also be expiries and various other claims or assertions in here. Now, the signature part, let's have a look at how this part works. So in the example we were looking at before, we saw that the algorithm was HS256. So in this case, it's an HMAC SHA-256. So let's take the header component, and we'll base64 URL encode that. Then we add a full stop after it. Then we take the payload, and we base64 URL encode that. And then we take that entire string, and then we run it through the HMAC SHA-256 hashing algorithm function of whichever language you're using. You might need to pull in a library for that. And you'll also need to provide a secret. So in this case, because HMAC is a synchronous hashing or encryption protocol, that is, there is one pre-shared key to be able to create the signature every time. The pre-shared key exists on both the identity server and all of the clients, all of the relying parties that you might log into. So if you've got an API, a front-end web server, and some other system in your ecosystem, they're all going to have to know this pre-shared key. Conversely, if you use something like RS256 or RSA SHA-256, this is a public-private key hashing algorithm. So we still take the header and the payload that have been base64 URL encoded, and we join them with a full stop. But instead of passing in this pre-shared key that every system needs to know, to generate the signature, you pass in a private key. And this private key only needs to exist on the identity server. And then with any kind of public-private key pair hashing or algorithms, there's obviously a public key. And that public key can then be stored on all of the systems that need to verify the signature. So you can probably tell at this point that there's a slight preference security-wise towards these asymmetric hashing or key hashing algorithms, because every system that needs to verify a signature can have access to information that is by its nature public already. Whereas in the HS256 or any of the symmetric key hashing algorithms, every system has to know this pre-shared key, so there's a higher chance of that information being leaked or being found out somehow. There are more issues, and that's what we're going to get into in a second. So now that we've got a basic understanding now of what JSON Web Tokens are, how they're generated, how signatures work, let's have a look at a few different ways that we could hack them to do stuff that they weren't designed to do, to bypass things. So 4 main categories, and I'm not going to describe them right now. We'll go through them one at a time. Let's jump straight into the first one, oopsie. So the oopsie one is what happens if the JWT signature is not even checked. Some of you might think, well, the protocol stipulates that there's a signature. Who's not going to check a signature? There are cases where it could just simply be oversight, or there are cases where it could be an actual bug in the application. I'll have a look at a little bug in a second, a potential bug. So just a heads up, get your brains warmed up, because I'm going to give you a couple of seconds in a couple of screens time to see whether you can find the bug. But before we do that, let's have a look at this search for JWT signature not checked in GitHub. So this is against all public repositories. And you can see that I've put double quotes around the not checked to make sure that I'm limiting to relevant search results for where JWT signatures are not checked. and we found 145 issues. And the first one there is actually from the Open Web Application Security Project repository. Now, I'm not saying that they have a bug. All I'm saying is that there is an issue in their project that contains the words JWT signature not checked. But I also haven't searched for JWT signature ignored or JWT signature not valid. So there are a number of other searches we could do to find more problems. But my point here is that there are problems being reported. Whether or not they're valid, we don't know. I haven't gone into that depth. But it's an issue or a concern that actually exists. Signatures not being validated in the first place. So I warned you there was going to be a little bit of code. I'm going to have a drink of water. And in the meanwhile, I don't believe I can get direct feedback from you, but I'll give you some seconds. And let's see if you can spot the bug in this code that means that the token is going to be returned regardless of whether the signature is valid or not. All right, a couple more seconds. And let's see whether you spotted this one. What we're doing at this point here is we started by grabbing the tokens, by taking the token and splitting on the dot. So then we've got part 0, 1, and 2, the header, the payload, and the signature. And then we recreate the signature. We take the header and the payload, and we recreate the signature using HMAC 256, using the pre-shared key. Regardless of what the signature actually is, though, we're now assigning the value of the signature we've just created back into the token. The equals is an assignment. So that should have been a double equals, or actually probably in most languages, a triple equals. So what we're doing now is we're saying the signature we just calculated, assign that back into the token, which is going to return a truthy. It's not going to return true, but the evaluation of this is true, which then means that we're just returning the payload. So the actual signature in the token got ignored because of this error here. So it might not just be ignoring it or forgetting to check. There could be a bug in the code that causes this to happen. Second thing, there's a way of experimenting with JSON Web Tokens. As with most systems, if you are doing something in development, there might be things you can do in order to make that development process or the testing process easier. So I mentioned that there are a number of algorithms that can be used for creating the signature. And in fact, there are 14 that are available if you have a look at jwt.io. I'll stick a link on one of the last slides for you, so you don't need to write that one down. But it's a website that lets you have a look into what's inside a JSON Web Token, but there's also a whole lot of information at the bottom of the page for a whole lot of different languages and tech stacks, for libraries, supported libraries, for JSON Web Token management, and the algorithms they support. And these are the 14 that most of them try and support. There's a 15th, though. And unless you've played with this in a development environment, you might not be aware of the fact that there's an algorithm type none. Now, some of you are probably already thinking, well, that's silly. If I can have no signature, then what's the point in having a JSON Web Token? There's no way of verifying whether or not the JSON Web Token has been modified. And in testing situations, maybe that's something you'd like to do, because you don't want to have to generate a signature every time you run through a huge number of tests. But what if this accidentally gets through into production? So let's take an example here. We've got so this is a representation sort of the JSON Web Token we saw before. We've got our algorithm, it's HS256. We've got our subject, our name, and our issue time, and we've got our signature. So the first two parts have obviously been base64 URL decoded, but that signature is the encoded signature that we saw before. And let's say we want to assume an admin role. So what we could do is come in and say, I'm going to add the admin is true into my payload. But then obviously the signature that will get generated is no longer going to match the signature that we have down at the bottom here. The signature here matches if this admin true is not there. So any correctly implemented application is going to look at this and say, signature is not valid. We can't use this JSON Web Token. But what if I change the algorithm to none and just remove the signature? Which would then leave us looking at a token like this. So the payload, you probably haven't noticed, is different to the payload we saw first time when we've removed the signature completely. Technically speaking, depending on how the none has been implemented in the application or in the library, you could probably still include a signature in there. But because it's actually a standard, there is a definition that says if you use algorithm none, signature has to be a zero-length string. So the last character of the JSON Web Token will be the dot. It's strange to think that this is something that's actually possible. you can understand why it's in there. But again, it's one of these things that if your configuration is incorrect in production, then suddenly you're able to use the none in a production environment, and that's not a situation we want to get into. And one of the things that this actually comes down to is that the header is also user-generated content. These JSON Web Tokens are sent via an HTTP request in the header of that HTTP request. So if it's coming from my browser and I'm sufficiently capable of finding that within memory in the application, or going through the network tab and trying to find it and modifying the request before I send it, I can change the JSON Web Token that gets sent to the end point. So we have to treat the whole JSON Web Token, the header, the payload, and the signature. We have to treat that as user-generated content, which, as we all know, should be validated. You wouldn't have a form field that doesn't have validated inputs. In the same way, the JSON Web Token needs to be validated. Next one, breaking the key. So if you think of the pre-shared key example for an asymmetric or HS, HMAC-based hashing algorithm, the pre-shared key is the same. It's passed around all the systems, right? So in essence, that's like a password. And we all know as software developers that passwords are probably the least secure credential mechanism. They can be written down, they can be repeated, they can be reused, they can be easily put into a big text file and shipped across the world to somebody else because there's been a data breach. There are all sorts of problems with passwords, and essentially a pre-shared key is a password. Now, yes, you can make them really long, you make them really complex, you can make them hard to guess, but it is still a password. So passwords can be leaked, as I've mentioned. They can be guessed, which is why you would probably want them to be really long and complex. But they can also be brute forced. And this is a really interesting point. If you have a web application where I log in with a username and password, to brute force a password and to try and log in as somebody else, I have to make a login attempt to your application every single time. And after 3, maybe 5, possibly 10, hopefully, attempts, your server is going to start throttling me, or maybe even saying, look, you can't do any more requests for the next 30 seconds or 2 minutes, or maybe my IP address gets banned. But because JSON Web Tokens have the signature built in, and the recipient can self-validate, it doesn't need a third party to validate the signature, you can actually brute force offline. So I could run a script on my laptop, and I've got a JSON Web Token that I know is valid. And all I've got to do is just generate every single permutation of any potential pre-shared key and keep trying to generate a signature until the signature matches, and then I know I've got the pre-shared key. So again, highly complex, very long pre-shared keys are good because it makes it harder to brute force. But you can brute force offline, which means you can't detect if somebody's trying to brute force. Now, I'm not trying to say here that HS or asymmetric hashing algorithms are a bad thing for JSON Web Tokens. It's just something we should bear in mind as developers, that this is something that could happen. Obviously, if you're using an HS256 based JSON Web Token in this situation, and you knew that your pre-shared key was extremely complex, then you can enforce things like an expiry of a certain time, so that by the time the key has been guessed, the token has expired. But that also wouldn't help, because I would just generate my own new token because I now have the key. So it's just some things that we need to bear in mind. And the fourth one, before we get into the demo, is tricking a system. So let's consider a situation where you try and downgrade the algorithm. This is not officially a downgrade attack in the true sense. So traditionally in a software encryption kind of environment, a downgrade attack would be trying to get a system to use an algorithm that was known to have a vulnerability. Now, what we don't want to do that, because there's no vulnerability as such in HMAC SHA-256. What we're trying to do instead is consider HMAC to be less effective than RSA, than asymmetric, because of the fact that there can be this pre-shared key, and that we could potentially regenerate it. But there's a side attack that, and every time I go further down this rabbit hole, it's becoming less and less likely that it could happen or actually get pulled off. But let's evaluate and have a look at what the situation would be in this example. So let's say that we're working on a number of different applications. We've started using JSON Web Tokens a couple of years ago, and we've got 3 or 4 different major systems, and we want to start consolidating a whole lot of code. So we start creating our own internal libraries for reuse within our applications. So we'll create a shared library, and into it, it's called decode, and into it we pass the token and a key. And then the library itself, or the function within the library, will say, okay, well, I've got a token, so let's have a look at the header of the token and have a look at the type and see what kind of token this is. Is it RS-256 or is it HS-256? Or is it one of the other 14, other 12? If it's RS-256, then we're going to call the RS-256 decode method, and we'll pass the token and the key in. And then the result will be the verified token based on the RS-256 hashing algorithm for the signature. If it's HS-256, we'll call the HS-256 decode method, etc. for all the others. This now means that if we make a change to the way we want to decode, we've only got to do it in one spot. And if we change the algorithm used by an application, we don't have to change every call. We just change the algorithm. It's changed in the header of the token. So it kind of self-heals almost. It's not really self-healing. It's probably the wrong term, but it helps us to create applications more easily. The whole point of a shared library. So let's now consider, we know we want a more secure kind of token. We know that the token is going to be shared with third-party systems, so we don't want to give them a pre-shared key. So we're going to go with an asymmetric hashing algorithm. We'll use RS-256, RSA SHA-256. And in here, we've got the subject, the name, and the issue time. And then we've got our business logic. And within the business logic, because we know that we're using RSA to SHA-256 hashing, there's a really convenient tool that most, if not all, but probably most identity providers support. And that's this part down here, the .well-known /jwks.json. So JWKS stands for a JSON Web Key Set. And what this means is that if you go to, in this case, this is my Auth0 tenant, but if you went to any Auth0 tenant or any identity provider tenant and went to .well-known /jwks.json, you would get a response, an HTTP response that contained JSON, that contained a list of public keys that were used or are the counterparts to the private keys that are used by that identity server. So in my application, when I push out this business logic, I can say, look, I just get the latest public key from the identity provider and use that. And that way, this is a bit of a sideline, if you have an issue at some point in the future and you need to rotate your keys because you think that one of the keys has actually been leaked somehow, you can do a key rotation. You don't have to roll out all your applications again because the applications are going to get the latest public keys from this endpoint. It's a convenience thing. It's quite cool. So we know we're using RSA SHA-256. So we go and grab the JSON Web Key Set. And from that, we get the public key. And then we can just call decode, pass in the token, and pass in the key. So what's going to happen at this point is our shared library is going to get called. It looks at the header, says, yep, this is an RS-256 algorithm. So we're going to call RS-256 decode, pass the token and the key in. That's great. So what could go wrong? What if I change the algorithm of my JSON Web Token to HS-256 and I add in admin is true? Now, in this particular case, what's going to happen is that the HS-256 case is going to be hit rather than the RS-256. So the shared library is now calling HS-256 decode and passing in the token and the key. But what's the key? The key is the public key that we got from the JSON Web Key Server, key set, endpoint. And the public key is a string, so it could be used as a key. So essentially what we're doing now is we're changing the application through this vulnerability to use an HS-256 algorithm to decode based on the key that's used in an RS-256 algorithm. There's a demo to this. So it's big picture thinking at the moment. We'll dig deep and we'll see how this works. And in fact, here's the demo now. So let's jump straight over. I've got this tool that I've been kind of working on. And basically what we have is we've got the JSON Web Token on the left here. If I make any changes to this, I'm not very good at writing in base64 URL encoded, but if I change that to a J, for example, there we go. That was a really good one. Sometimes I do this and the application breaks. Let's just change that to an I. If I change this back to an H for HS-256, you'll see that this gets fixed back here again. So whatever I do over here will update the actual JSON Web Token. And I can also use this tool here to regenerate this signature based on an HS256 algorithm. And if I take this request and I submit it, it goes to a backend, and we can see that it's received this token. So that's basically exactly the same token that got sent in, got a status 200, and we know that the admin value is currently false. And what we want to do is try a number of different ways to log in as admin. So the way I would log in as admin is to change my name to admin. That's how this application determines whether or not I'm an administrator. If I submit this request, I'm going to get an invalid signature because this signature here doesn't match the hashed version of these two combined. So, and also before we do that, let's just double check this one. So I can also submit this request and that comes 200 again. If I change the pre-shared key that's used and regenerate the signature here, this will also fail because the signature is invalid. So let's just go back, check that one still works, and it does. And then I'll go back and I'll change this one back to admin, and we should get the error again. Excellent. So let's just jump in and have a look at some of the code. You don't need to understand JavaScript. You don't need to understand React, which is the tool that I've written. As long as you've got a bit of a concept around coding, you'll be able to walk through this with me and we'll see what's going on. But essentially, when I click on that submit button, this submit request function gets called. And what I'm doing is I'm making an HTTP request to an API function, and the API function is called request. And into there, I'm passing in this authorization header. So remember how I mentioned that a JSON Web Token is passed in as the header of the HTTP request. So the header name is authorization, and the value of the header is the word bearer, followed by a space, followed by the JSON Web Token. And this is one of the reasons why the JSON Web Token is base64 URL encoded, to make it URL safe so that you can add it into your authorization header and it doesn't break with things like quotes and stuff all over the place that could then, or new lines, or things that would break the request. So the JSON Web Token gets passed in this way. And essentially all we do, we're also saying that the content type is going to be JSON. And the response of that, we're basically just going to put into the value of set result, which is just this part of the bottom there. So that's kind of the key of what's happening in the React app. If we look at the request page itself, basically I've written 4 different request handlers so that we can look at the 4 different examples, and we just export whichever handler I want to use at the moment. We're going to start with a regular request handler, the one that actually does decode HS256 requests. And that looks a little bit like this. We don't need to look at this one at all, but basically what we're doing is we're pulling out the bearer token. We're verifying that the token is valid. And up here, we're using the JSON Web Token library to be able to do this. We'll have a look at this one later. That's going to be the last test. So let's come into this one here. And I now want to disable the regular one and enable the ignore signature. So this is this example where the signature is ignored either because there's a bug in the application or because there was an oversight during development. And in this case here, as you can probably imagine, as soon as I hit request, we should get a 200 OK. There it is, and admin is true. And that's basically because it doesn't matter what the signature is. It's just being ignored. So, and as we've seen, it's something that could potentially get into code quite easily. And the number of times that development level code gets into production unnoticed is higher than it should be. Let's put it that way. All right, let's have a look at the next example. So this one is where we allow none. So let's save this. So what I want to do now is I still want to log in as admin, but I know that the signature is being checked. But if I come in here and I change this to none, and then I remove this altogether. So remember how I said before, the last character would be the dot. So now we've got a very short JSON Web Token. Algorithm is none, name is admin. If I submit the request, we can see here still we get status 200, and we get is admin is true. Now, just to double check, if we'd been using the regular request handler, then this would come back as a signature is required. So it's not even invalid now. Signature is required. And then the last one. So those are somewhat obvious. You can kind of tell what's going to happen there. But the trusting algorithm one was a little bit more complicated to kind of describe. So let's go through this one and see what actually happens. So if we could just come into this tips tab here. This is a tool that I want to make public at some point. It's kind of half public already. Join me in the AMA afterwards. I can share a link for you to play with this, or at least the GitHub repository. But I want to make this something that anybody can just load up that's hosted and play around with. So there's some tips here to help people get started. If you ever wanted to do something and playing around with RSA key pairs and you didn't want to go through the hassle of trying to remember the command line tools for creating RSA public-private key pairs, there's a tool here to create them for you. Now, obviously, this is somebody else's server creating public-private key pairs for you, so it should only ever be used for demos. Never use any keys generated by a third party in your production environments, because by default, somebody else already has your private key because they generated it for you. But for demos, absolutely perfectly fine. Go to this URL. We've got the public key here for convenience. So this is the public key that gets checked by the application. And we have a correctly signed JSON Web Token for the user Ben Dechrai. So if I copy this and we paste this in here, we'll see the generation function, the signature generation has disappeared because we've got an RS-256 algorithm and the name is Ben Dechrai. So here's a valid admin login. So what I want to do now is I want to change this to admin, which is now invalid. But there's no way that I can work out how to recreate the signature without having the private key. And there's no way I'm going to get that private key. So what I'm going to do instead is I'm going to change this to HS256, at which point it's now going to expect an HS256 signature. So my tool has re-enabled the ability to generate a signature based on a pre-shared key. So remember when we were looking at the code, it was passing in the token and the key. And if it was an RS-256, it would use token and key. And if it was HS-256, it would use token and key. So for an RS-256, the key would be this public key here, right? So if we copy this, and we paste this in here, and then we regenerate the HS-256 signature, this signature here is a signature for this content based on this as a pre-shared key, not as a private key, or a public key, rather. It's taking this as the password, the pre-shared key, for generating an HMAC SHA-256 signature. And if I then come in, I'm just going to double check that I hit save over here. I did. If I then come in and I hit submit, we now get is admin is true, and status is 200. We're still logging in with a symmetric, but remember, we're actually using the key from an asymmetric hashing algorithm to recreate the signature so that the application then thinks that the token is valid. So these are all real-world scenarios. These have been seen either through testing, through like the good people testing and trying to find bugs in systems. I can't say whether or not they've been used in real life to actually circumvent for malicious purposes. I'm sure they have, but they've definitely all happened in hypothetical research kind of environments. So things that we need to look out for. So that's pretty much it for the demo. I hope it's been enlightening to see how it can actually go wrong. And this, as I say, I'll share the code with you as well. But I don't want to leave just on a note of, hey, look how wrong things can go. So let's have a quick think about what we can do to make sure that we are validating JWTs correctly. Remember I said that a JSON Web Token, and you've now seen that a JSON Web Token that gets passed in a header is essentially just user-generated code, or user-generated content, rather. The same as filling in a form in a web page and hitting submit. You can't trust that data because it's been 100% created by the user. The JWT has been 100% sent by the user. All of that data could have been modified by the user. It's been generated by an identity provider, but we don't know that it hasn't been tampered with. So we can't trust things like the header. We have to ensure that if your application wants to use an RS-256 hashing algorithm, then you have to make sure that it will never believe an HS-256 header, if that makes sense. So don't reinvent the wheel. Use proven libraries. And there are some of the things that the libraries will do as well is in the example I just showed you where I used the private key as a signature, there are libraries that will try and work out whether or not sorry, I said private key, a public key. We use the public key to generate the signature. There are libraries out there that will try and determine whether or not that is the case, so that it can detect things like this. The advantage with any of these libraries is they're pretty much all open source. The link at the bottom of the screen here, jwt.io, is the one that I mentioned before. It's written by a colleague of mine. It actually looks a little bit like this, only it's a lot prettier. It doesn't allow you to hack the JSON Web Tokens, but it allows you to look around inside to see what's going on with the JSON Web Token. And if you scroll down a bit further in that page, that's where you'll find the list of all of the different tech stacks and platforms and the libraries for them that have been written by various open source providers, and also the hashing algorithm compatibilities that they have. And if you do find that you're using any of these libraries and they don't quite do what you need, then as with all open source software, fix it, push it back into the main repository, give it back as a pull request so that everyone can benefit from it. Or rather than writing it again, if it's not quite what you need, talk to the developer, the owner of the main package, and see if there's any way you can help it to make it better. General open source guidelines there for that most of you are probably familiar with anyway. So that's pretty much it. I'd like to thank you for your time. I won't take questions right now. We will be jumping over to an AMA in Discord. But before we leave, I would like to thank you all for your time. And also, I'd love to get your feedback on how this talk went, how much you got out of it, whether there's anything that's still unclear. We are giving away T-shirts to people who fill out this form. So if you go to a0.2/feedback-ben, we will select the top, the first 10 people who fill out this form. I'll send a T-shirt to. I'd love to do it for the whole hackathon, but I'm not made of money. So the first 10, I will send a T-shirt to. Thank you for your time. I think I've been joined again in the channel, and I'm looking forward to chatting to you in the AMA. Thanks.
Thank you, Ben, for coming in, and it was a beautiful session indeed. And as we told everyone, how you structure the concepts and how you deliver them is really beautiful.
Thanks.
So thank you all for joining in, and now hope to see you all on the Discord server. We can have an awesome AMA. Thank you.
Awesome. Hopefully I can get in. I'll see you there.
Ashwin?